All right, starting chapter 4. This is called antiderivatives. This symbol kind of looks like an S, which the book does much better than I do because I am artistically challenged. Is called an integral. It means antiderivative, and we'll explain more of what it's used for later. But for right now, let's just talk about how to do it. So if we take the integral of a derivative, what we wind up with is the original function. We usually say the original function plus some constant c, because as you remember, if we take the derivative of a constant function, we wind up with 0. So we don't know if there was a constant, wasn't a constant, exactly what it was. So we always put c if we're doing what's called indefinite integrals. Again, don't worry about the word indefinite yet. We'll get to definite integrals later. But for right now, we're going to put c on the end of them. So in general, let's talk about the rule. So if we take the integral of x to the n power with respect to x, this is what this dx means. The integral of x to the n dx means take the integral of x to the n with respect to x. So basically, we know that in a derivative, we bumped the exponent down. So we're going to go backwards. We're going to bump the exponent up in an integral. And that means we're also going to have to multiply by its reciprocal out front so that it'll cancel out. And again, this is that c that we talked about that may or may not have been there. So an example would look like this. If I took the integral of x to the third with respect to x, it'd be 1/4 x to the fourth plus some constant c. Okay. Notice if we take the derivative of this, if we started off with the function f of x is equal to 1/4 x to the fourth plus some constant c and took the derivative, we'd wind up right back where we started at this x cubed. So that's one way to check. Have I taken the integral right? You take the derivative. If you wind up back where you started, you've done it correctly. Okay. There are no such things as product rules or quotient rules or chain rules with integrals. We'll get to some things later, and again, I'll explain those later. But for right now, anytime we have constants or anytime it looks like it might be a product, we're probably just going to rewrite it for right now. So here's a constant. Here's one thing you can do. If I have 3x squared dx, I just take the 3 out front. I go ahead and take the integral of x squared dx, which, again, we talked about that rule before. We bump it up by 1 and we multiply by its reciprocal plus some constant c. And in this case, the 3 and the 1/3 will cancel out, x cubed plus c, and this is x cubed plus c is the integral of this. Again, if you'll go backwards, you'll notice that this would be 3x squared if I took the power rule derivative, and that's exactly where we wound up again. Some trig. Since we know that secant squared is the derivative of tan, then it must be the case that the integral of 2 secant squared x dx is just going to be 2 tan x plus some constant c. Let's talk about one where we may have to rewrite. So if we want the integral of square root, for example, we have to rewrite that. So this is the integral of x to the 1/2 with respect to x dx. So then we bump this 1/2 by 1, which makes it 3/2. We multiply by its reciprocal, which I know I wrote this out kind of silly, but we know that the reciprocal of 3/2 winds up being 2/3. So we've got 2/3 x to the 3/2 plus some constant c. So sometimes we have to rewrite. Okay. A differential equation involves having a derivative, and you can solve if you have what's called an initial condition. So again, I made this a little tougher than I probably should have. However, h prime of x is equal to this x plus 1 times x minus 2. Initial condition of the original function has a value of 3 at h equals -1. So let's talk about the antiderivative first. First of all, I go ahead and use the FOIL method and I knock this out. We don't have a product rule for integration, so I go ahead and use the FOIL method and knock this out. Then I use that rule that we just talked about. Bump this by 1, multiply by reciprocal. Bump the x1 by 1, make it x squared, multiply by the reciprocal. This just becomes an x, and I have plus some constant c. So now what? Well, I take h of -1 and I say the y value has to be 3. So everywhere I find an x, I put in -1 instead, and I almost forgot my c in here, and I plug this in. So this is 1/3 minus 1/2 plus 2 plus c equals 3. I converted them all to sixths. So -2/6 minus 3/6 plus 12/6 plus c is 18/6, or 7/6 plus c is equal to 18/6, or that constant was 11/6. So the original equation, instead of being 1/3 x cubed minus 1/2 x squared minus 2x plus c, was actually 1/3 x cubed minus 1/2 x squared minus 2x plus 11/6, with the initial condition that h of -1 had to equal 3. We're going to cover something more in class called slope fields, and we'll get to that in a little bit. But here's some homework that if you want to spin down, or if you want to take a look at it as I put it into the folder for chapter 4, which I'll have to create. But here's the homework that we're going to wind up doing on Tuesday. And thanks, and have a good weekend.